Yeah, thanks, Martin, for its introduction. So yes, so my topic will be the portable linear solver for high-order spectrum elements with GPU. And with the portable, you might already expect I need to talk some top 500 again, like the other talk on Monday and Tuesday. So for like the top 5 supercomputers, except from the first one, the Fugaku ones, they all equipped with the GPU. But you might also notice they are equipped with different vendor GPU. So we will have some portability issue in the supercomputing. So this picture is the performance share from the top 500 now. So the black box here is still some supercomputer use the CPU parts. And in the red box using the AMD GPU, and blue box use the Intel GPU, and the rest use the NVIDIA GPU. So in this top 500, we know somehow like if you only focus one vendor GPU, you only get maybe 1/4 or 1/3 performance in top 500 here. Always the wrong way. So we need to deal with the portability. So there are two way to deal with. You can use some like the portable language, or like you use the native language for coding your kernels here. So like the portable language, you can use the OCA, Cocos, OpenCL, OpenMP, and SQL. But then there are some pro and con here. So like if you use the portable language, you only need to write one code base, and then you just try to compile for different GPU, and then you can. It's also reduce your maintenance because you only have one code base here. But definitely it requires another abstract layer. And also sometimes it might impact your performance. Yeah, but also from yesterday, I also learned sometimes the impact here maybe not the baseline. Sometimes it can perform better than the native language. It's somehow quite interesting here. And then definitely you can still use the native language. Here is somehow language they use from the vendor. So you use the CUDA for NVIDIA GPU, or keep ROCm for AMD GPU, and SQL or one API for Intel GPU. You get the benefit from definitely you can always get in touch with the cutting edge feature, and you should expect the best performance if you're coding pretty well here. But to maintain that, you definitely have different code base, and then sometimes in documentation you have different technique term to need to understand. So it will also introduce some maintenance effort. You want to keep this, and as I said, it's the work in the NetEye. So main talk is already explained. So I only roughly have one slide to conclude this. So it's somehow like fast and scalable. CFD code and targeted HPC application, and you can see like you can do some cross simulation in a pretty large scale. And NetEye is relying on the OCA portability layer to run on different GPU here, and like the NVIDIA or AMD here. And Ginkgo we use another way. So they in NetEye they use the portability language, but we use the native language. So first of all, we extract, like you write your pseudocode, or like you write something in the MATLAB here, you have the algorithm in some like the pseudocode here in the code, but you need something to run this code explicitly on different backend to ensure our sustainability. So first we have the single thread implementation, so it should be easy to understand, and you can easily to check the correctness of the reference code here by the CI/CD here. And then we move on to different accelerators. So we use the OpenMP to write the optimized code for the CPU, and CUDA for NVIDIA GPU, and HIP for AMD, and PBC plus or SQL for the Intel GPU. To ensure the correctness, we always compare the result from the accelerator code to the reference code to ensure everything is correct, even if you are on the GPU. So for now, we try to connect them together. So NetEye currently you can use the OCA or MGX or Hyper to solve the code script problem. And for now, from Ginkgo side, we also support previous in Sundial, MFAN, or OpenFOAM. as another GPU backend in this different application. And this talk we make the connection between the Ginkgo and NetEye here. So we add the Ginkgo as another option. And in the NetEye, they will perform the P multiply here, and then we our effort is change the code solver. I bring different solver option to the code solver in the NetEye here. So Ginkgo we already have we focus on the sparse linear solver, so we already provide a lot of functionality in terms of the sparse linear algebra. So we definitely have a lot of metric format and like several kinds of the Creo solver, like the CG by CG step or GenRes. And definitely we have some advanced preconditioner like Jacobi or PAR-IOU or IOUT, and also some incomplete sparse process inverse we can use in Ginkgo. And then there are some different applications that require different functionality. So we also have the batch on the top right. So if you application have many small systems, but they share the same sparsity, we can reuse the sparsity for all the problems to reduce the memory footprint to improve the performance. And also we have our own MG and also some sparse array stuff. And there's one thing I missed to change. So for now, AMG also supports the dispute patient. So you will also see some benchmark in the later comparison. Yeah, so we already make the integration to the NetEye. It's pretty easy to configuration. So like sometimes you cannot find the solver quite easy. You need to try different solver to see which one is best to fit your problem. And in current integration, you just need to specify, code solver need to use the Ginkgo, and then you can provide the config file to configure your solver. So for example, we can have like on the left side is the conjugate gradient, and I want to run up to 4 iteration, or if it reach the time to power -4 in the residual number reduction, it stops earlier. Or another one, we can have the MG with different code-saving method and then just run 1 iteration here. So in the practice, you just need to switch your config file in your in the config file from the NetEye, and then you can try different solver easily without recompilation. So yes, so we come to the experimental now. So we use the garbage and RBC benchmark problem now, and we consider 3 options as the code solver configuration. So first is smoother from NetEye. It should use the Jacobi with the Chebyshev, and then the conjugate gradient from Ginkgo, and the algebra multigrid with the conjugate gradient as the code grid solver inside the MG. So it's the different code grid from the NetEye currently. And we run this experiment on Eureka. Each node contains 4 NVIDIA A100 GPUs per node. And we run small length just to make sure it's a bit long-term running. We do not just measure some overhead in the beginning. So we run more than 3,200 time step now, and we report the timing from the 3,000 to 3,100 time step here. Yeah. So garbage 6 is used 16 for distribution per point per in each dimension here. And the blue one is the Ginkgo with CG, and then Ginkgo, the red one is the multi-group with CG, and then the yellow one is the smoother from the OCA. And the green one is use the Ginkgo CG as the strong scaling to filling, and we run the experimental from 4 nodes, 7 nodes, and 14 nodes. And in the 14 node in the right hand side, Ginkgo CG can get still gets roughly 1.1 speed up compared to the NetEye smoother here. And then we increase the digitalization point per each iteration, per each dimension. So it's for now it's garbage 128. And then we overall still like Ginkgo CG has the best performance on this like 40, 55, and 110 nodes here. And in the end, we still have the same 1.1 speed out compared to like the previous plots here. But here we have seen some different stories. So smoother have a better strong scale behavior now. So originally it's slower than with the less node, but it can be faster than Ginkgo multiple with the country gradient when we use the 110 nodes here. And then in RBC, it's designed for HDC, you need to run 14 nodes here. We run 40, 80, and 120 and 160 nodes. So in the right-hand side, in the rightmost side, we run up to 116 nodes. So it will have 340 GPU here. And it's quite close together, so it's only like 5% speed up you can get from Ginkgo CG compared to the smoother. And next, we have larger gap, and in the 80 nodes cases, so it's run 80 and 120 and 160 nodes in these cases. So we have seen some big gap compared to the previous one. So we have 1.15 speed up in the end compare like the Ginkgo CG compared to the smoother. And definitely we still see, and also here is a bit different story compared to Gabri's 128. So here is like the Ginkgo multi-grid with CG gets better in the 116 nodes here. So here is the strong scalability is better than the smoother in these cases. So you might, in the RBC case, we somehow run normally like 40, 80, and 160 nodes, but in Garbage we have a bit weird setting. So we run the Garbage 64 from 4, 7, and 40, and the 128 we from 15, 5, and 110 here, because we try to make the problem generate such that the average local size is same in each node, such that we can have the weak scaling with different setup, and we don't need to rerun the NPI again here. And then we have the weak scaling efficiency here. So overall, it's quite similar, except for the small cases from 4 node to 28 in the smoother is lower than the Ginkgo CG, but when you get enough nodes, you will expect the similar weak scaling efficient from NakedIce and Ginkgo, like roughly 70% of the weak scaling efficiency here. Yeah, and just to prove our portability, so we do not have the access to the some like the AMD supercomputing, but we have self-host the server with 8 AMD GPU here. So it's almost like the toy example here. So we just run it as the showing we indeed can run on the AMD GPU here. And then, yeah, come to the conclusion. So we showing like we integrate the Ginkgo as the another option in the NakedIce now. So you can try not just try the OCAD, you can also try Ginkgo with different solver setting inside the NakedIce. And we show the performance. It's more focused on the NVIDIA GPU, showing like you have like country gradient as an option. You can get maybe 10% speed up here. And unfortunately, we only show some like toy run in the AMD GPU. And definitely, we bring many different linear solver options to the NakedIce now. And for sure, like future, Ginkgo itself already support the mixed position. So we would like to try the different mixed position scheme to the NakedIce, see if we can get any benefit without facing the convergence issue inside NakedIce. And definitely, we want to get the better solver configuration for different kind of application. Yeah, it's the acknowledgement from the for scale, and thanks, Yulik, for the supercomputing resource. Yeah, thank you.